Hello everyone, I'm Qiaochu from the University of Washington. Today, I'm presenting our work, RASSAR, Room Accessibility and Safety Scan in Augmented Reality. In this work, we propose a system called RASSAR, which semi-automatically scans indoor spaces for accessibility and safety issues. Here on the screen, we see a carefully designed home space, and it might be a nice living room in many people's eyes. However, that's not the situation for everyone. For example, when a wheelchair user visits this place, they instantly faces unreachable spaces in this room, as well as doorknob that is too high that's also unreachable. That's not the only case. For older adults with weaker leg muscles, the cozy-looking sofa is too low for them to stand up. For blind or low-vision people and children, the sharp edges and corners might be dangerous. And for all these communities, the unsecure throw rug may trip them. The risks are so common, but we cannot see them. This common neglect creates unfairness in our indoor spaces. We believe that safe and accessible home space is a fundamental human right. However, past research shows that over 90% of housing units in the US are inaccessible. Similarly, 98% of newly built homes in the UK are inaccessible to wheelchairs. As most people live in pre-existing spaces, which requires careful auditing and renovations to improve safety and accessibility, we are in great need for easy and affordable ways to audit indoor spaces. Luckily, the recent development of computer vision and mobile devices have enabled us to conduct real-time indoor object detection that helps us find accessibility and safety-related objects in indoor spaces. Additionally, LiDAR sensors, which tracks the traveling time of light and provides depth information of scene, are introduced to many phones, which further helps indoor understanding. Using these tech, phone can now gain deeper understanding of the indoor environment, capture information about what objects are in the room, how big they are, and also where they are. This makes it possible for us to build a phone app that scans home spaces, detect and visualize accessibility and safety issues, which is the RASSAR tool. To design RASSAR, we went through a design process involving prototyping and a formative study. We first built a technical prototype using AirKit, Apple's Room Plan API, and YOLO object detection model. This prototype enables real-time detection of accessibility and safety issues and visualization of them in AR. This prototype reaches 90% detection accuracy in our test, showing the great feasibility of our technical pipeline. Based on this positive result, we further conducted a formative study among 18 participants across 5 key stakeholder groups, including wheelchair users, older adults, families with young children, blind or low vision people, and occupational therapists. Each participant is interviewed for about 1 hour for their accessibility needs and indoor auditing practices. We also showed our prototype to solicit feedback and suggestions on design improvements. We found out that 16 out of 18 participants were favorable about our RASSAR prototype. We also observed common sources of indoor accessibility and safety issues, such as stairs, doors, and floors, hinting on our list of accessibility issues to detect. We see disparities in accessibility and safety concerns across communities, highlighting the need for RASSAR to be customizable to address the different abilities and needs. Additionally, we found out that none of our participants and with accessibility needs chose to use accessibility checklists in their own auditing practices. Besides these qualitative findings, we also provided some design probes to invite stakeholders to express their design preferences in the UI/UX of the RASSAR app. With these improvements, we present the RASSAR system, which is now an iOS application. Let's quickly see how RASSAR works. RASSAR's user interaction starts with selecting target accessibility communities. By selecting one or multiple user communities, we could provide customization to users' specific accessibility needs. After selection, user scans the indoor space with phone and gets real-time feedback about the indoor reconstruction shown with the minimap that rotates with user's facing direction, and about detected accessibility and safety issues like table height, throw rug, and scissors, shown with pop-up icons. The user could click any icon to show more details about this specific issue, then either confirm this issue and get back to the scanning process, or deny this issue and remove it from the scanning process. To assist blind or low vision users, the user interface is designed to work with VoiceOver.
VoiceOver on, RASSAR. Voice assistance. Switch button. Choose your communities. Wheelchair user, but wheelchair blind/low vision, blinds, older adults, older children, button, children, start scanning, button.
And we also provide a custom audio assistance option. When enabled, RASSAR provides real-time audio about the scan process, objects detected, and issues found, and also a summary of findings.
Start.
Please point camera at top and bottom of wall to initialize. Table. Detected throw rug. It's a tripping hazard. Table. Share.
Finish button.
Scan finished. We detected 3 issues in total.
Currently, we support 4 categories of issues. Object dimension, like a table being too high or too low. Object position, like an electric socket being too high or low. Risky items, like throw rug and sharp objects. And lack of assistive items, like no grab bars near toilets. After the scanning is finished, user could use a button to end the scan and get a 3D reconstruction as a summary of the scan results. User could pan, zoom, and move the 3D model to inspect certain parts, and click any object to see more details. In general, RASSAR does 3 things. It identifies the problems in indoor spaces. It localizes the problem to exact 3D spaces and show them in augmented reality. It displays information of the problem and provides helpful suggestions to users. When scanning, the RASSAR tool scans home space with LiDAR and camera and processes the data stream with an object detection model trained on a 2500 image dataset we collected, and also Apple's Room Plan API. This results in a parametric room reconstruction containing information like object label, position, and dimension. Based on these info, we can run accessibility and safety rubrics to detect issues. To make sure we're not misleading our users, we incorporate multiple professional sources of accessibility standards, including the ADA design guidelines, research papers, as well as several widely used accessibility checklists. These sources, as well as our formative study findings, form a 20-item accessibility and safety rubric list, each with respective relevance to our 4 target accessibility communities. The detected issues are then visualized in AR in real time. We conducted 2 studies to verify RASSAR's performance and usability. First, we ran technical evaluation over 10 home spaces, including 7 apartments and 3 houses. For each space, we conduct 3 scans and compare the detection results with manual auditing. The performance is evaluated with accuracy, consistency, and scanning time. The results show RASSAR being precise, robust, and consistent. The scans, which on average takes around 1.5 minutes to finish, are also way faster than manual auditing, which can take more than 30 minutes in some cases. Besides the technical evaluation conducted by our research team, we also pay visits to our actual stakeholders' homes and invite them to use the RASSAR app. By comparing their scanning results with the manual auditing results, we can see that the average accuracy is comparable to our technical evaluation, which shows the app being highly usable, and also the scan performance doesn't rely on expertise in scanning. The participants also highly rated RASSAR's usability. Please see our paper for more details in evaluation. In conclusion, we propose a phone-based indoor accessibility and safety scanning system and verify its performance and usability. For future work, we plan to keep improving the detection performance and the scope of accessibility issues. We also envision this indoor auditing framework being used in more than just home spaces, but also public spaces. Thank you.